This note today is a direct follow-up to that lab that you were asked, and hopefully you finished a couple days ago while you were working on momentum and some other energy topics. The whole thing behind springs is something called Hooke's Law. So obviously named after an old white dude that discovered it a long time ago. In hindsight, it seems like a pretty easy law. So I think any of us, had we been alive at the right time and had the right amount of influence at that time, we probably could have come up with Hooke's Law, because the math on it isn't too groundbreaking, but it's called Hooke's Law, and the expectation is coming out of grade 12 physics that you can kind of do the math on springs. We're going to follow up Hooke's Law, so spoiler alert, our next topic in this is something really cool called simple harmonic motion, which is all about springs and how springs can make things vibrate. But for now, just Hooke's Law. Hooke's Law talks about the behavior of, in physics, what we're going to call an ideal spring. An ideal spring is one that just sort of behaves nicely. It's not really heavy. Like if you had a slinky in your house, if you held the one end of your slinky like vertically, then the bottom end would sort of get pulled by its own weight and stretch the spring, stretch the slinky. That's not an ideal spring. An ideal spring isn't so heavy that its own weight causes it to stretch. And kind of more importantly, an ideal spring, it doesn't have what we call internal forces that you have to overcome to make it start to stretch. If you've got an ideal spring, if you pull it a little bit, it stretches a little bit. There are springs out there, like maybe you have a spring that pulls a door closed in your house, or I don't know where else you'd have springs in your house, but sometimes springs, if you just pull on them a little bit, they don't actually stretch. And you sort of have to overcome this little bit of threshold force to make them stretch. Springs with that sort of threshold before they start to stretch, those wouldn't be perfectly ideal. The lab that you did, the ones that we're going to talk about in class, because we got to start somewhere, we're going to start with the easy ones. We're going to start with ideal springs. So basically what Hooke's Law is what you guys saw in your lab. Here's a little version of the graph here. Hooke's Law, and this is the part I got you to focus on in the lab, is if you stretch a spring, so it's calling it load. Actually, this one's kind of sideways from how you did it. This one put force on the x-axis and distortion on the y, but it's a linear relationship. The force is proportional to how far you stretch it or squish it. So let's say you've got an ideal spring. If you squish it a little bit, you're going to get a little bit of force. If you squish it twice as much, then you're going to generate twice as much force. Similarly, like with stretching, stretch it a little bit, you get a little force. Stretch it a lot, or stretch it 3 times as much, you get 3 times as much force. So it's a linear kind of thing. Hooke added a little bit. It is linear, but if you go too far, then out here, the graph stops being linear. So there's a little bit of a curve there. That's called beyond the elastic limit. If you stretch it too far, we start losing that linear part. And if you stretch it too far, so up to here, then it'll break. There was a time when I taught grade 12 physics where I could say, remember the Slinky lab? Because at SGM anyway, every grade 11 class, we make you do the Slinky lab. So unless you're absent that day, everybody coming out of grade 11 would have done the Slinky lab. In these crazy COVID times, since we didn't get out too much lab equipment in grade 11, some of you may not have done the Slinky lab. But if you did the Slinky lab, the Slinkies we have in the school have been abused over the years. They don't go back to their original shape. They've been stretched too far. They've been twisted. They've been tangled. If you've got a spring like that has sort of been overstretched, that means you've pulled it beyond its elastic limit. So the Slinkies that we use in school, a lot of them have been stretched beyond their elastic limit. So they don't go back to their original shape. We haven't had any break in class, but that would be the next step. If you stretch a spring too much, then it's actually going to break. So that's all that Hooke's Law is the force that a spring creates is proportional to how much you've stretched or squished that spring. In physics, the force that a spring creates we call the restoring force. Really what that means is if you've got a spring and you squish it a little bit, then the force that it creates is trying to get it back to its original shape, trying to restore it to its original length. So if you squish a spring, the force it creates is outward, trying to make itself longer again. if you've got a spring and you stretch it longer, like in the lab by hanging a mass and pulling the bottom of the spring down. If you pull the bottom of a spring down, then the restoring force that creates is going to be upward. They call it restoring because it's trying to get it back to its original shape. If we go back to the lab, to the concept, or even just a math class, if we know that force is proportional to the stretch or squish, to go from a proportion to an equation in math, we would add a constant, or if we could do a lab and graph it, it's the slope of that graph. So the graph I put in my note had force and distortion in the wrong place compared to how we did the lab. I had you do the lab the way you did so that we could match the equation that Hooke got. So if you do the lab the way it was typed, you put force on the vertical, so force kind of replaces the y, distortion or s kind of replaces the x-axis, then y equals mx plus b, the b ended up being 0, we get y equals slope times x, or f instead of y, k is replacing the slope, s instead of x. My little legend down here, capital F is always force. I don't know why I'm writing it since I already typed it. I called it S because it's the stretch or the squish. If you Google it, you'll see sometimes sources call it X for the amount of distortion. K is the new thing. K is the letter that gets given to the slope. It's not the most imaginative letter to give this. Maybe capital H for a Hooke would have been smarter. I don't know why. But K basically, it's a number to tell you how stiff the spring is. If you've got a spring like in the end of your pen, that's going to have a fairly low spring constant, a low value for K. Every car has got springs in the shock absorber system. There's other stuff in there as well, but if we just focused on the springs in the shocks of your car, that would have a huge K value because it takes a lot of force, basically the weight of the car and then some, to start distorting those springs. So K we're going to call the spring constant, and it's just a number that tells you how stiff the spring is. It doesn't have any fancy units. If we rearrange K, if we rearrange it all by itself, is F divided by S. So it's got the units of newtons divided by the units of the S, which is a distance, which is going to be in meters. So the K, the spring's constant, is going to be a number, and it's in newtons per meter. That's part of Hooke's law. The second part of Hooke's law, and this is what we did when we came up with that weird gravitational field energy equation. A part of physics, we didn't use it in grade 11, but a part of physics is the energy of a system is the area under the force versus distance graph. So this is maybe a little bit too general. If we can graph force versus distance, the area underneath that is the energy in the system. For gravity, instead of calling it D, we called it letter R. For springs, we're going to call it letter S because it's the stretch or the squish. So from the lab, you all had the graph. F here, S down there. That's what your graph looked like. I'm just going to say this is some arbitrary S, this is some arbitrary F. In physics, if we could find the area under that graph, that tells us the energy stored in the system. For the gravity one we did last week, it was a little bit ugly because it wasn't a nice shape. This one's a totally nice shape, so it's easy for us to find the area. The math is all there, but I'll talk you through it. E for energy equals area. It's a triangle, so the area is going to be 1/2 base times height. The base, got my 1/2. The base is S, how far we've stretched the spring. The height is F. If we stop there, that would be our equation for the energy in a spring. It's 1/2 the S multiplied by the F of the spring. But we could go a little bit further. We just figured out that F is K times S. So the outcome of the lab I was hoping you got to was that force is equal to K times S. Force is equal to slope times the distortion. You might not have called it you might not have called it K, but hopefully in the lab you said force is equal to slope times distortion. The other one that you might not have got to because it required the substitution is that the energy stored in a spring is 1/2 k s squared. For now, that's all there are to these ideal springs. You need to become comfortable with working with those two equations. If it's a question and the concept involved is forces, the force a spring creates is the spring constant multiplied by the stretch. If it's a question that involves the concept of energy, the energy stored in a spring is 1/2 ks squared. I'll yabber on about the energy just a little bit more and then I'll turn you loose to try those examples. In the old days, like the way back when Hooke was alive and doing his work, they didn't really have good batteries. So a spring would literally be a source of energy. Classic example is old school watches. They would wind the watches in the morning, storing energy in the spring, and then that energy would be released slowly over the course of the day, keeping track of the time, moving those gears in the watch. If you've got a garage door on your house, if you peek, usually it's above the garage door in the current model of garage doors, there's a big monster spring up there. It's kind of a different spring. It's a twisty spring, but it's the same logic. There's energy stored in that spring. So when you go to lift the door, instead of using the electric energy of your garage door opener or the energy out of your body, if you're just manually lifting a garage door, the energy stored in that spring helps you do the work. It exerts a force over a distance and the garage door is easier to lift for you because you don't have to spend as much energy or put in as much force. So springs literally were like old school mechanical batteries, a way to store energy. If you squished a spring, it's got some joules in it. You could eventually use that spring to, I don't know, in some of the questions I talk about shooting a Nerf dart or shooting a toy car or whatever spring might be used for to push things around. Springs literally, once you squish them, store energy. So I think that's enough talking for me for now. You need to be comfortable with these two equations. The force generated by a spring is K times S. The energy stored in a spring is 1/2 ks squared. In the note, so when you guys scroll down, when you guys look down, there are 4 examples down here, and they really just work through whether using F equals K times S or E equals 1/2 ks squared. So I suggest you read through them, think about what concept is involved. This first example, my wife loves to travel and she always puts way too much junk in her suitcase and they weigh a ton. So imagine a suitcase hanging from a spring, not unlike the lab you did. What concept was involved in that? That'll tell you which equation you use. Is that a force Ks equation or energy 1/2 ks squared equation? So what I'd like you to do is work through those 4 questions, and then there's a worksheet and a check-in to go with it. As always, email if anything's bugging you.